This video, we're going to work through some examples using the LogicWorks digital simulation platform. So in LogicWorks, we've already started it here. We can simulate digital logic circuits of nearly any sort. So we've just started the program, and first we'll come to this window which says Welcome to LogicWorks. And to start, we're just going to create a circuit. This gives us our canvas where we can start placing digital gates, and we have a timing window here. Initially, let's avoid using the timing window, so we can minimize this by going to Window and turning it off. Now, when we wish to place digital logic gates on our canvas, we need to use the part library here. Now, what we can use for simulation is somewhat limited. So when we click here, we've got several libraries that we can choose from. The libraries that are most of use initially are simulation gates and simulation I/O. So let's click on simulation gates. Simulation gates gives us access to AND gates, NAND gates, here, NOR gates, the NOT gate, some OR gates, XOR, among others. And you can experiment with these. XNOR as well, XOR. It is also possible to have inverted inputs. So if you have an OR gate here, we can invert both the inputs, an OR2, two input OR, and we have two inputs inverted here. And to place a logic gate, we can double click here and place. And that gives us our logic gate, and we can place as many as we like. So I'll place 1, 2, 3, for instance, and then press escape. Now, if I don't want these, I can just use Control Z to take these off, and they disappear. So let's try implementing a simple logic circuit. I'm going to come here to Microsoft Word, and let's say we want to implement the circuit y equals a, b prime, or c. Let's highlight this, Control C to copy, and then we come back to LogicWorks, and then we can paste our copied text into our canvas here in LogicWorks. Y equals a, b prime, or a and b prime, or c. So we have an AND gate, an inverter, and an OR gate required. Let's do this here. We have three input variables, so let's draw these. We will first come to the wire tool here, and let's draw an input variable. Double like so. And then we can highlight this and copy and paste like so, and we can place for as many input variables as we like. So space these wires 2 apart first of all. So we've got A, B, and C, and now we need to label these. So we will come to the naming tool here and click on just the very edge. Call this A. Click on the edge here and call it B. Click on the edge here, call it C, and we're done. Now, I'm going to undo this for a moment. Just an example, if I miss the edge and type C, and then look here closely, the color is black versus the magenta color for the wire label. The wire, if it's not labeled appropriately, it will appear as black, and then the connection will, well, the wire will not be labeled properly. So make sure that you name the wire appropriately and that you don't miss the connection. So now that we've placed 1, 2, 3 input variables for A, B, and C, we need B inverted. So we are in simulation gates. We're in the simulation gates library. Let's go to the not gate. N-O-T. And let's place it here. Now we can connect this to B, and this gives us an output variable, B prime, from here. So let's draw our wire again. The reason that we are drawing and not copying from here or from here is that we would be copying a net with the same name, so we have to label it again. So we connect, and now we can label our output variable, B prime, like so. So now that we have A, B, C as our input variables and B prime as our output variable inverted with this inverter here, we can now place an AND gate for the two input AND. A ANDed with B prime. So AND 2. Let's bring this in. So A ANDed with B prime. Now we need to OR how many inputs? Well, we have this quantity, A ANDed with B prime, ORed with C. So we need 2 inputs. So we will take an OR 2 and add this to the schematic. And then we connect A ANDed with B prime, and then OR that with C. This will give us an output Y here. So we can label this Y. So it's nice to draw the circuit, but it's even better if we can simulate it. So let's click on the list of libraries here and select Simulation I/O. Simulation I/O, our input is going to be a binary switch. So let's double click and then place 1, 2, 3 binary switches for 3 input variables. Now if we wanted to, we could drag a wire across here and connect it like so for A, B, and C. This is one method for connection. Another method, I'm going to undo these 3 connections, is we can use virtual connections by labeling the outputs of these binary switches. Let us name them. A for a virtual connection with the A bus, B for a virtual connection with the B bus here, and C for a virtual connection with the C bus. Finally, we can look at the value of the output variable Y by using a binary probe. Let's double click and place it here. Now a Z represents a disconnected input. That means there is no input value. However, when we connect Y, here we should have an output value. And we are getting Z right now, so we're going to start the simulation here. If you see a Z on the output, even though you have all connections, sometimes the simulation is not started, so you can click Run Simulator. And now that we are running the simulator, we can see that we have a 0 on the output here. A is 0, B is 0, C is 0. So 0 ANDed, 0 inverted is 1. ANDed with 0 is going to be 0 here. C is also 0, so 0 ORed with 0 is 0. If C is equal to 1, however, then 1 ORed with anything. We don't care what this is if C is equal to 1. So let's set C equal to 1. We should see an output of 1 at Y regardless of the value that we place for A and B. So if A is 0 or 1, it's not going to change the output. Watch the output value. B, if it changes, it doesn't change the output value. So if both A and B are 1, it doesn't change the output value here to 0 at all. So when C is 1, we see that Y is always equal to 1. What about if C is 0? Well, this is only going to be 1 now. Assuming C is 0, Y will only be 1 if A ANDed with B prime is 1. So A must be 1 and B prime must be 1. Therefore, B must be 0. So if A is 1 and B is 0, we get an output of 1 all the time, regardless of whether C is 0 or 1. If A is equal to 0 at all, then and C is 0, then regardless of B, it will always be equal to 0. If B is equal to 1, B prime is 0, so regardless of what value we have for A, this value will not change at the output. We will always see 0, assuming we have an input of 0 on C. One nice property I showed earlier, we could copy a value from Microsoft Word and then place the Boolean algebra expression here. So it copies as graphics. If we were to run Excel, we could place a truth table here. A, B, C. And then an output Y. Let's center all 4 of these columns. And then we can highlight these. Let's give it some color. And then we can highlight all input combinations. Would be 8 possible input combinations and the header, so we need 9 rows. Right click, properties, format cells. So let's add a border here. Border, outline and inside. Click OK. And now we can enter all our possible input combinations. 0, 0, 0. So for all possible input combinations of Y equals A, B prime, or C, let's take a look. Y equals A, B prime, or C. This should be 0. For A equals 0, B equals 0, C equals 0. What about for this entry, A, B, C equal to 0, 0, 1 respectively? Well, C is equal to 1, and therefore we don't care about the value of AB prime, so, because 1 ORed with anything is always equal to 1. What about for A equal to 0, B equal to 1, C equal to 0? C is 0, so we need to look at AB prime. A is 0, so 0 ANDed with anything is 0. 0 ORed with 0 is 0 again. Here, C is equal to 1 again, so we're going to place an entry of 1 because we don't care about the value of AB prime, because 1 ORed with anything is 1 again. A, B prime, A is 1, and B is 0 here. 0 inverted is 1. 1 ANDed with 1 is going to be 1, and 1 ORed with 0 is 1. For this case, C is equal to 1. 1 ORed with 1 is 1. A is equal to 1. B is equal to 1. B prime is 0, so 0 ANDed with 1 is 0. 0 ORed with 0 is 0 again. Finally, here, C is equal to 1, and we know that 1 ORed with anything is 1, so we have our final table. Now that we have our truth table, we can highlight it and copy. And when we come back to LogicWorks, we can paste it as a truth table in our canvas. This is a raster graphic, and being able to place truth tables like these and Boolean algebra equations into the LogicWorks schematic can be very, very useful for understanding, so don't hesitate to use that feature. Now, sometimes you'll notice that there are logic gates that have some number of inputs, like 2 input, 3 input, 4 input, 5 input. And so this is all very nice, but then it jumps to an AND 8. So what if we wanted an AND 7 or an AND 6 instead of an AND 5 or an AND 8? Well, in this case, we may want to use a constant input to simplify the gate to a smaller number of inputs. So ORing with a constant 0 or ANDing with a constant 1 would be one possible solution. Let's go through a simple example here. File, New, and we'll create a new circuit. And let's say we wanted, for simplicity's sake, we wanted to have an AND 3. Now, we'll place this here, and we will place simulation IOs. We'll place 2 binary switches here and here. And let's label first our outputs. We'll call this A, and we'll call this one B. And then we'll label, let's start from the middle, A, and then we'll label this one, label this one A, and then label this one B. So we have connections from A to A and B to B by virtual connection because they have both the same label. Now, for speed, I'm going to go to Simulation, and I'm going to click on Show Values. So the Simulation pull-down menu and Show Values. Now what we see is Z, 0, and 0 for our inputs. I can move these a little bit out of the way here. And move these out of the way and make them a little bit more visible. And we can see here, we don't want to move the label. Let's keep that really close and just move the value. So A is equal to 0, 0, B is equal to 0, 0, and we have a Z input here, which means it's disconnected. There's no digital value 0 or 1 there. However, it is outputting a 0 on the AND gate. So this is happening because 0 ANDed with anything is always equal to 0. So it doesn't matter that we have a Z input here. Let's try setting both A and B to 1, however. When we have A and B both equal to 1, then suddenly we have a Z ANDed with 1, ANDed with 1. That would be 1 and 1 is 1. 1 ANDed with Z is going to be undefined, so we get an X value. This is, generally speaking, an error condition. You don't want to see X's if you can avoid it in most cases. So if we wanted to use this 3-input AND as a 2-input AND, we would need to place an input 1 here. So this logic input 1 would come from simulation. We'll pick from the library, connectors. And you can choose plus 5 volts here and place it here. And then connect it to an input on the AND gate. Watch the output of the AND gate when I release. And we have an output 1. There's a Z here. This is a quirk of LogicWorks. I'm going to turn off the show values option and then show values again to turn it on. And notice that we have 1 and 1 and 1. So all three are input to 1 and we get an output value of 1. Let's look at all possible input values of A and B. So for the AND gate, we should see an input or an output of 1 if and only if A and B are both equal to 1. So AB is 0, 0, AB is 0, 1, AB is 1, 0, AB is 1, 1. So iterating through all four again, remember to watch the output. It's 0 for 0, 0, 0 for 0, 1, 0 for 1, 0, and then 1 for 1, 1. This is because we have a 1 here on the input of on the third input of the 3-input AND gate. For the OR gate, we can OR with, or let's try looking at the OR gate, for instance, simulation gates. Let's try an OR 3. And now I can place labels for A and B here. Let's move the values out of the way. Like so. And now we have 1 ORed with 1 ORed with Z. 1 ORed with anything is always equal to 1, so it doesn't matter that we have an input Z here. However, if we have both 0 and 0, or 0 for A and 0 for B, then we have 0 ORed with 0 equal to 0. We would expect a 0, but because we have an unconnected input here, we will receive an X. We will receive an X at the output here. So, going to connectors again, we can tie a logic 0 to this input by using a ground symbol here. Let's connect it. And we see 0 or 0 or 0 is equal to 0. And anytime A or B goes to 1 or both, watch this, it changes to 1, changes to 1, back to 0, changes to 1, back to 0. Both of these are 1, it's 1 again. And this is how you would use a ground to do a logic 0 or a plus 5 volt to do a logic 1.